Okay, so now I'm going to do the same that I just did for the Cartesian case and apply to the case of polar coordinates. Remember that in polar coordinates, the idea of polar coordinates is that if you have a point x comma y, then instead of specifying the point with x and y, you want to specify the point with r, which for us will always be considered as a positive number because it's just the distance from the origin. So this is just going to be the square root of x squared plus y squared, which again we'll take to be positive. And you also specify the angle with theta. And theta, again, if you do like a right triangle here, you can see that the tangent of theta is y over x. So theta is the arctangent of y over x. Okay? Or if you prefer, you can also write them in the way which you typically do, which is that x equals r cosine of theta and y equals r sine of theta. Okay, so that's what polar coordinates look like. And the first thing that you can do, similar to the Cartesian case, is just draw. So you see now x and y are functions of r and theta. So you can try to draw the curves that correspond to points with constant r or curves with constant theta. So what does that look like? Well, curves with constant r. If the r is constant, that means that the distance from the origin is fixed. And what are the curves with the property that if you take any point on that curve, the distance from that point to the origin is the same? Well, that's basically the definition of a circle, right? A circle is a curve where all the points on the circle are the same distance to the origin. So the curves of constant r look like circles, center at the origin. So this is constant r. Right, so any of these curves represents a curve where r is constant. And then you can also ask, well, what are the curves with constant theta? So any curve, what is a curve with constant theta? It would be a curve where the angle of the points with respect to the x-axis hasn't changed. And if you think about that, that just means that you are on a segment or array, better, like more precisely, it's array emanating from the origin. So any of these curves, any of these segments, is a curve where theta is constant. Okay, and you see this is like well, basically it looks like a radar, what you would see on like on a radar, you know, on a submarine. But the point is that now this sort of partitions or breaks the xy plane naturally into these sectors, okay, which are the ones that I'm coloring right now. And our goal is to try to find like an estimate for a formula for the area of one of these sectors. So we're trying to find what would a tiny amount of area of one of these sectors be? Okay, and so that's what I'm about to start discussing right now. So in order to do this, let's just remember what we did in the Cartesian case. In the Cartesian case, what we found were the velocity vectors of the curves. In that case, the curves were like either horizontal or vertical lines, so the velocity vectors were just like I or J. But like these curves also have velocity vectors, so let's just try to figure that out first, because it would be useful to see what's going on. So just to illustrate what I'm trying to do, let me choose a very specific value or a very specific point, which is say 1, 1. Okay, so if you choose 1, 1, right, the distance from the origin of 1, 1 is square root of 2. So the circle that passes through this point this would be a circle of radius 2, of radius square root of 2. So that means that if you take any other point on this circle, x comma y, well, we're saying that r, which is the distance to the origin, has to be root of 2. So it becomes root of 2 cosine of theta, and y becomes root of 2 sine of theta. So you see, in this case, again, you get a position vector for this point on the circle, which depends now on theta. Let's call this r sub c, c for circles, because these curves are giving us circles, whose formula is root of 2 cosine of theta, root of 2 sine of theta. On the other hand, we could also look at the curves, at the curve with constant theta that passes through this point. Again, remember that those curves are just a rays. So you will get this ray. The reason why I chose this with pi over with 1, 1 is that it's easy to see that the angle has to be pi over 4. Okay, so that means that if you have a point x comma y here on this curve, now r is the thing that can change, but cosine of theta becomes cosine of pi over 4, which is 1 over root 2. So you get r over root 2, and sine of theta becomes 1 over root 2, so you get r over root 2. And again, you get a curve which now depends on r, so let's call this r for ray, okay? Or, well, let's call it a for angle, because the angle is fixed. So, which depends on r, which is r over root 2, r over root 2. We have these curves. Now what I want to do is compute the velocity vectors of these curves. That's not too bad. It's just what you get after differentiating with respect to the corresponding variable. Again, think of this as being time and time. It's just that now t, we're not calling them t, but rather r or theta. So the velocity vector for the first curve, this one, the constant angle, would be found by differentiating with respect to the variable r. One way to write it is like this: 1 over root 2 times 1 comma 1. Okay, and so as you can see, it's just basically 1 comma 1 is still essentially if you think of 1 comma 1 as a position vector for this point, this means that this velocity vector is just a rescaled version of this position vector. I guess here slightly smaller. So if the position vector for the point here is pointing away from the origin, then this rescaled version is also pointing away from the origin. Let's call this vector, let's say A. Okay? And in the other case, the variable is theta, so that's playing the role of time. And so you get this vector. And let's call this vector V. And basically, how do you know how this vector looks like? Well, it's not difficult to check that what's the dot product between A and B. The dot product between A and B is 1 over root 2, 1 comma 1, dot that thing, so dot root 2 minus sine of theta cosine of theta. So the square roots cancel and you get negative sine of theta plus cosine of theta. I think I'm doing something. Let's see. Okay. Oh yeah. That's fine. Right. Good. This is okay. This is a formula. But this formula, it depends like on the angle, because we haven't. I'm still I haven't drawn the vector, like the things like the vector A was the same along all these points on the ray. Okay, but the vector V is actually changing because it's supposed to be tangent. So like if you want to compute their dot product, really what I'm doing is evaluating at a specific point. Say I'm computing the dot product here because we were starting the point 1 comma 1. So at 1 comma 1 the angle was theta, and so this is 0 when theta was pi over 4. Sorry, that's what I was trying to say, because sine and cosine are the same. Okay, so at this point the vector that I drew is they are perpendicular. Okay, and let's try to see if that's true in general. So in the general case, what happens if it's not 1 comma 1, what you're working with, so in the general case what you have is, let me put it like this. In the general case, when you look, instead of 1 1, well, Think of this point as being on the right. Let's call this point x naught, y naught. Okay? So that has some distance r naught and some distance theta naught from the origin. So this point is just, again, any point here is a point of constant theta, okay? So it's just, since theta is constant, this point is just, r is changing, so this point is of the form r cosine of theta naught, r sine of theta naught. Okay? And for this point, any other point here of this curve, now they are with constant radius, so theta is the one that's changing, right? So this point, the radius is r naught, so it's r naught cosine of theta, r naught sine of theta. Okay, and so what I'm trying to say, I don't want to erase it here so that you see the comparison with this case. You still have a vector r sub a. This is what we were calling r sub a of r. Okay, the derivative with respect to r of r sub a of r happens to be still cosine of theta naught sine of theta naught. So it's just a generalization of this case. It's just here that I had evaluated when theta naught equals pi over 4. And the derivative with respect to theta of r sub c of theta, right? It gives you, like, you're just differentiating the trigonometric function, so r naught is constant, so you can pull it out if you want. So you get minus r naught minus sine of theta cosine of theta. Okay, so that means that if you do the dot products, right, you still have this vector which we can still call a if you want, which is here. And then you have this vector which I'm still calling b, which again, this one keeps changing because it's tangential to the curve. And so if you do the dot product of a dot b, then this gives you what? A dot b gives you r naught minus cosine of theta naught sine of theta plus sine of theta naught cosine of theta. And again, this is 0 if you compute the dot product between these two particular vectors. So this is 0 if theta equals theta naught. In other words, if you choose an arbitrary point, the velocity vectors of the curves for r constant and theta constant are perpendicular. This is what I was going after. So why is all of this useful? Let's go back to our original question in case you forgot about it. say you had two circles. You had two angles, right? And so there's like a region of this sector, and we're trying to compute a formula for the area of that sector. Okay, so imagine that you start with the point x naught, y naught here, which again had distance r naught and angle theta naught with respect to the origin. So if you move along, again, if you move along this line in the velocity with the velocity vector given by this vector a, right, remember that the velocity vector there was the tangent vector here was called a. Then the displacement, let's call this r naught. Then a displacement here just is again this depends on r, so this is like the t. So the displacement here, like instead of delta t, you would talk about delta r. So you can in some amount delta r think that you moved a times delta r. Okay, and so you end up with this vector, this larger vector, which is a times delta r. Let's put it here so that it's closer to the, here it is, a times delta r. Okay, on the other hand, you had this other vector b, remember that they were like they were perpendicular at this point, a and b. So in in this case, the thing that's playing the role of time is theta. Okay, so that means that you move, the displacement that you would move is velocity times delta t, or velocity times delta theta. So you can move some amount, and let's say that this gives you velocity times delta t, or delta theta, which is in this case. So what I'm trying to say is that since these two were perpendicular, right, like the green one and the yellow one were actually perpendicular to each other, basically you can sort of think that you have you can try to draw like a rectangle here. So you have a rectangle of sides b delta theta. Now let me draw it so that it's more accurate. You have a rectangle where one of the sides is one of the displacement vectors is a times delta r. And the other displacement vector is v times delta theta. And then the area of a rectangle is just the product of the norms. So like the area of this rectangle would be the norm of a times the norm of v times delta r. Times delta r times delta theta. Sorry, these delta r's had no arrows on top of them because those were like the changes in time. So, but now what is the norm of A? The norm of A, this is a unit vector, so that's 1. And so this is 1 times norm of V, but norm of V is R naught times delta R times delta theta. Okay? And then the argument is that really, as whenever you make these delta R's and delta theta smaller and smaller, there's not that much of a difference between the area for the rectangle and the area of the circular sector that we were trying to compute. So the area, the point is that the area of the entire thing, the area that we were actually interested in computing of the circular sector, what I'm trying to say is that you're trying to approximate it by the area of this rectangle, and so that just happens to be well, R naught, but like really you can just call it R because R naught was arbitrary. So you get R times delta R times delta theta, and this is why in the limit, which is what you see when you write in an integral, in the limit you get the formula for polar coordinates that dA equals R dr d theta. So that's like the explanation for why the formula in polar coordinates, where the formula for dA comes from in polar coordinates. So what we will do in the next video is just talk about the general case and see how this is supposed to work.